All right, so we now look at hexose sugars. Yeah, one of the common types of monosaccharides, right? Yes. So just like we already said, hexose sugars are simply 6 carbon sugars, and they have the formula C6H12O6. So this is the general formula for hexose sugars, right, guys? So that is the general formula for hexose sugars. So we also need to know that these are also direct source of energy, okay, for cells, of course, and they are oxidized during cellular respiration, okay. And we also need to take note that among these hexose sugars, since we have got 3 of them, okay, glucose is the most common respiratory monosaccharide, okay. Yeah, we have got 3 extra sugars that we are going to talk about in this video, which will be glucose, galactose, and fructose. So among these 3, glucose is the most common respiratory monosaccharides. Guys, let's take note of that. Let's take note of that. Okay. Yeah, let's take note of that. Okay. And these, they are also used. Yeah, we'll talk about this point. Yes. Hexose sugars are also used in synthesis of disaccharides. Okay. Yeah. Oligosaccharides and polysaccharides. We'll talk about these, guys. Don't worry. Don't worry. Yeah. Since we said that on hexose sugars, we are going to talk about glucose, um, galactose, and fructose. We'll simply start with glucose. Okay. Yeah. So we'll talk about under hexose sugars. We'll talk about glucose. So we'll talk about glucose, galactose, and fructose. Okay, we'll talk about these 3. All right, guys. So let's start with glucose. Yeah, let's start with glucose. Let's start with glucose, guys, without wasting much of our time. Glucose. Okay, well, glucose is also known as grape sugar. Okay, yeah, so glucose is also known as grape sugar. We need to take note of these, guys. Okay, yeah, and it is found in plants. Okay, so it is found in plants. All right, yes, guys. All right, so this glucose is simply a product of photosynthesis. Okay, this is the product of photosynthesis. You need to take note of these, guys. Yeah, glucose is an important product of photosynthesis. Okay, yeah. Also, glucose act as a fuel. Okay, a fuel for cellular respiration. Okay, let's take note of this, guys. Let's take note of this. Okay, yeah, so this is glucose, guys. All right, So glucose is actually soluble in water. Okay, it's soluble in water. All right, guys. Why is glucose soluble in water? Well, it's soluble in water because of its hydroxyl groups. Okay, yeah, that form hydrogen bonds with water molecules, thus leading to glucose being soluble in water. Okay, and also we need to take note that the open chain form of glucose is an aldehyde or an aldose, yeah, whose carbon 1 combines with the OH group of carbon 4, okay, of the yeah of carbon 5, right, to do what? To give a 6-membered pyranose ring. So this forms a pyranose ring. Okay, so it forms a pyranose ring. So let's take note of that, because for pentose sugars, 5 carbon sugars, then they form they form a pyranose ring, right? Those they form a furanose ring. So these they form a pyranose ring. So glucose forms a pyranose ring, galactose forms a pyranose ring, but there is an exception of fructose. Fructose, despite of it being a 6-carbon sugar, it forms a furanose ring, just like pentose sugars. We'll discuss this as we proceed. Okay, yeah, amazing. Okay, so we also need to take note that glucose is a powerful reducing agent. Okay, why? Because of the presence of the aldehyde group at carbon 1. Okay, yeah, we'll talk about this. All right, yes. So the same glucose, okay, has got the D form and the L form. Well, the commonly occurring glucose is the D isomer, okay, while the synthetic L isomer is commonly used as a low calorie sweetener and as a laxative. Okay, those luxury things, yeah. Hope, yeah, I hope we are together. But let's take note of this, okay? But living organisms cannot use L-glucose as an energy source because they do not have an enzyme to break it down. Is that clear, guys? Please, let's take note of that. That's the reason why even in today's lesson, we're not going to talk about L-glucose. Yeah, we are going, rather we'll focus on D-glucose. Okay, because we know that when we know the structure of D-glucose, we can simply swap some things to get the L-glucose, which is very simple. Okay, yes, guys, this is very simple. Okay, so without wasting much of our time, let's simply jump into the structure. Okay, the structure of 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 D-glucose. Okay, the structure of D-glucose. We're not going to talk about L-glucose, but D-glucose. So, well, we know that this is a 6. Okay, a 6-carbon what? A 6-carbon sugar. So it's supposed to have 6 carbons. 1, 2, 3, 4, 5, 6, guys. Okay, for this one you can even put it like this, or the other way, it's still fine. Alright, guys. Okay, so you simply start with an H here, then here you put an OH, right? Okay, you come here and put an OH, okay, OH. You come this side and put an H. From there, this side you put OH, OH. This side you put H and H. This is D-glucose. Okay, how do we come up with L-glucose? Well, it's simply by swapping. You get everything which is here, you deflect them this side, and everything that is here, you deflect them the other side. Then you've come up with L-glucose, right? So this is D-glucose, guys. This is D-glucose. Okay, yeah, this is D-glucose. But how does glucose and galactose, which we are going to talk about, differ? Well, glucose and galactose only differ on carbon number 4. Okay, so this is carbon number 1, carbon number 2, carbon 3, carbon number 4. So on carbon number 4, this OH group is this side in galactose, and the H is this side. So they swap here on carbon number 4. So when you swap on carbon number 4, you get galactose. That's the only difference between glucose and galactose. That's the difference. Okay, yeah, or should I say one of the difference. All right, amazing, guys, amazing. So now let's draw the ring form of G glucose. Okay, yeah, let's draw the ring form. Okay, so this in ring form, it will form this thing. So it will be like this, huh? Since it is a 6 carbon. Okay, have you seen? I hope we are able to see, guys. 1, 2, yeah. So here there will be carbon, oxygen, yeah, oxygen. Okay, guys. So now, if we put the OH on top here, okay, if we put the OH on top here, if the OH is on top and the H is down on carbon number 1, it means that this is the B form. Okay, so what will be the name of this? Well, the name of this will be B what? D what? Gluco, right? So it will be gluco from glucose, from, right? Gluco what type of ring is this? Pyranose. Okay, so it will be BD gluco pyranose, right? So gluco pyranose. All right, are we together, guys? Let's finish filling this ring. So now on carbon number 2, as you can see, carbon number 2, the OH will be, so these will be outside, huh? So the OH will be here. What will be inside is the H. On carbon number 3, here we have H, here we have OH, right? On carbon number 4, here we have the OH, and here we have H. Okay, yes, guys. What about here? Okay, the oxygen here would have reacted with this, so we'll have H down there. Okay, as you can see, yeah, H. Then we get this thing and put it here, so it will now be H2, but you write it like this, right? Yeah, it's just one and the same thing. Okay, so that is how you come up with the ring, guys. That is how you come up with the ring, guys. Okay, yeah, so what simply happens is this will react with that. Okay, yes, I hope we are together, guys. I hope we are together. Okay, so let's now draw this is the B form. Okay, yeah, let's now look at the L form. Okay, so this structure is the open chain. This is what they call the open chain, and this is an aldose because the carbonyl group is at the terminal here, right? What about this? This is the closed ring. As you can see, it's a ring, closed ring. Okay, yeah, closed ring, which is the pyranose in this case. Well, let's draw this is the B form. Let's draw the alpha form. Okay, so yeah, these will only differ on carbon 1. It means that the OH now will be down for it to be called the alpha. So it will be alpha D glucopyranose. Okay, then everything else guys remains the same. Everything else remains the same, guys. Are we together? Are we together, guys? Are we together? Amazing, amazing. Okay, hope everything is clear, guys. For now, hope everything is clear. So this is it about glucose. All right, guys, so this is it about glucose. This is it about glucose. Let's now look at galactose, right? Yes, so let's now look at galactose, guys. Galactose. Well, guys, galactose is also a water-soluble monosaccharide, just like glucose. Okay, and it is a structural isomer of glucose. Let's take note of that. Yeah, we'll find structural isomers as we continue learning, right? Yeah, so the only difference is that in glucose, okay, on carbon number 4, right, the OH group, as you can see here in glucose, right? So this is carbon number 1, 2, 3, 4. So on carbon number 4, the OH group is down here in glucose, okay? But in galactose, the OH group will be up there, okay? Yes. The same thing applies here when we come to the straight chain, right? What will simply happen on glucose, as you can see, the OH group for D, we are talking about D, we're not talking about L. For D glucose, the OH group is this side. So in galactose, it will come this side and the H will come this side. That's the difference. Okay. Galactose also forms a pyranose ring. Okay. Yeah. But it differs from glucose only on carbon number 4. Okay. Yeah. We also need to take note that galactose combines with glucose to form a dimer called lactose, which is a disaccharide. We'll talk about disaccharides, right? Because currently you are on monosaccharides. Yeah, lactose is also known as milk sugar. Okay, yeah, and it is present in milk. Okay, well, let's look at the structure of galactose. Okay, yeah, because galactose is just similar to glucose. So we'll draw the same structure for glucose. We only swap on carbon number 4. So it will be like this, guys. So 1, 2, 3, 4. Carbon number 4. Okay. So go on carbon number 4, right? And swap. Meaning that instead of having the OH group this side, the OH group will be this side. And this side will have the H. Everything else remains the same, guys. Everything else remains as they are. Okay. So everything else, guys, remains as they are. So this is the open chain form of D-galactose. D-galactose. Okay. Yeah. When you want to turn it into L form, just bring everything which is here, reflect them the other side. Everything which is here, reflect them the other side. Then you come up with the L form. Okay. Well, what about the ring form? Well, the ring form will be the same as will be similar, right, to this for glucose, right? The only difference would be on carbon number 4, right? Yeah. So let's simply draw. So when the OH is on top here at carbon number 1, this becomes the B form. So it will be what? Well, it will be B, since this is a D form. Yeah, D what? Galactopyranose, right? Yes. So it will be galacto what? It forms a pyranose ring, so it will be galactopyranose. All right, guys. Yes. Okay. So everything else. So we'll go on carbon number 4, right? Because we know that the only difference between glucose and galactose is on carbon number 4. Yeah, one of the differences, right? So the OH group on carbon, on glucose, since it is down, here it will be up. So this OH group will be up then, and then everything else remains the same. Okay, if you want, you can get it from here, just one and the same thing, right? So it will be on carbon number 1, you have your OH here, then hydrogen there. Carbon number 2, carbon number 3, you have your H here and your OH inside. Okay, what about here on carbon number 4? You have your H here and your OH there. What about here? Well, this would have reacted with this, right? So here we'll have the H as usual. Have this thing on top. Okay. Yes. Hope everything is clear, guys. Yeah, this is the B form. Well, what about for the L form? The only difference between the B form and the L form is on carbon number 1. Okay, so this is carbon number 1, 2, 3, yeah, so carbon number 1, 2, 3, 4, 5, and 6, right? Yes. So now guys, let's just draw the alpha form. So the difference between the alpha and the beta is on carbon number 1. So the H group, since is up in B, to be down in alpha form. Everything else remains the same. Okay, so alright guys, so this is it, and this one will be called alpha D galactopyranose. Alright guys, so this is the closed ring structure and this is the open ring structure. Yeah, the open chain structure. This is the open chain structure, not open ring, right? Yes guys. Okay, amazing. Okay, so now we now move to fructose, right? So we've talked about glucose, galactose. We now move to fructose, guys. Fructose. Okay, all right, so now move to fructose. Okay, so this is now fructose. So well, we need to take note that yeah, fructose is a water soluble monosaccharide. Okay, it is soluble in water and it is found in things like in honey, in fruits, flowers, berries, and in root groups. Okay, excuse. Yeah, so now what we need to take note is that unlike glucose and galactose, the open chain of fructose is a ketone or a ketose whose carbon 2 combines with the OH group of carbon 5 to form a 5-membered furanose ring. So this will form a 5-membered furanose ring, unlike glucose and galactose, which forms a 6-membered pyranose ring. Okay, yeah, and it is also used as a source of energy in cellular respiration, just like glucose and galactose. But fructose, unlike glucose and galactose, is a weak reducing sugar because its open chain structure is able to isomerize. Okay, yeah, we'll discuss what that means. Okay, yeah, so the idea is its open structure is able to isomerize actually into an aldose sugar. Okay, so it is able to form something like glucose. Okay, yes guys, that's it. um okay, so Let's simply draw the structure. Yeah, the structure of fructose, the open structure of fructose. So fructose is like this. Okay, starts with this. Okay. Then we have the carbon, another carbon, another one, another one. Okay. And we also have this thing again. Okay. So this is fructose, guys. But its carbonyl group is not at the terminal end. That's the reason why it is called a ketone. Okay. As you can see, the location of the carbonyl group. Okay. Yes. Right, guys. Right. Okay. So yeah, this is it. Its structure is actually similar to that of glucose. Okay. In other words, that's the reason why I've opened this structure for glucose. Okay. So when you see, immediately you draw this, okay, there are some things that you just need to include, okay, which are similar to that of glucose. As you can see, this part for glucose, this part for glucose, this part for glucose, guys, okay, that part for glucose is the same one which you are supposed to put here. Okay, then you've come up with fructose. Well, so this part here, you just get it and paste it here, so it will be like this, guys. Okay, are we together, guys? Are we together? So this is the D form. So this is D fructose. Okay, hope we are together, guys. Hope we are together, guys. Okay, so this is D fructose. All right, if you want to come up with the L form, you know what to do, right? Just swap everything, which is this side, the other side. Yeah. Okay, so now let's draw the ring form. Okay, the ring form of fructose, because we know that fructose, unlike glucose and galactose, it forms a 5-membered um, furanous ring, right? Just like pentose sugars. So this is actually the structure. So we'll start with a B form. Though the drawing for these is a bit different from those of pentose sugars. Yeah, just like you can see, guys, Yeah. Okay, so let me also draw for the one for I don't know, but my drawings ish. Plus I'm using a pen, so immediately I make a mistake, I cannot rub. Okay, yeah, look something like this, guys. Okay, yeah, something like this. All right, so well, our oxygen will be here. All right, so if we take this as the B form, the OH group will be up there. What will be down there, unlike for glucose and galactose, what will be down here is simply this thing, which is the CH2OH. Okay, all right. Then here we are going to have the OH will be inside. Then here we'll have H. Okay, yeah, OH. I don't know how you're going to write it, but yeah, that's the thing. Okay, what else, guys? So here you have CH2. Then yeah, okay, amazing, guys, amazing. So just like you have seen, so it's all about the procedure is the same actually, because as you can see, yeah, the H, as you can see, this is the H, right? It's here. The OH, it's here. Okay, this would have reacted, so the H would have remained, blah blah blah. Okay, so the same is true for, so this is the B form. Okay, this is the B form, so the name will be BD fractofuranose. Okay, well, what about for this one? The difference will be on this carbon, right? Where the OH will be down, what will be up is the CH2OH. Everything else remains the same. Everything else, guys, remains the same. Yeah, so this will be called the alpha D fractofuranose. Okay, this is the open chain form, and this is the ring chain form. Yeah, this is the ring form. Yeah, this is the open, so this is the open chain form, this is the ring form. All right, guys, all right. Okay, so before we move to disaccharides, we can simply uh, talk about hexosisomers. Okay, yeah, we can briefly talk about hexosisomers. Okay, well, what are isomers? Isomers are simply molecules that have the same molecular formula. Okay, so the molecular formula is the same, but they have different arrangement of the atoms in space. Okay, examples of monosaccharide isomers include you've got optical isomers, which are simply the molecules which rotate polarized right to the right or left. Okay, which one are these? I've got the D form and the L form. For example, D glucose and L glucose. Well, we also have stereoisomers. Okay, so stereoisomers are simply molecules which have got the same molecular formula and the structure formula, but differ in the spatial arrangement of atoms in molecules. Examples of this, we have got the alpha form and the beta form, as you can see. Okay, so this alpha and the beta form are simply stereoisomers of each other. Okay, what about these D? Because we said, for example, when we come here, this is the D form, right? Yes. But when everything which is here, we put them the other side, the other side, it becomes the L form. So between this D form and the L form, these are optical isomers. These are called optical isomers. Okay. When everything is, when polarized right is rotated to the right, it forms the D form. Okay. Yeah. When polarized right is rotated to the left, it forms the L form. Okay, what I simply mean by that is